We are going to use PID loop simulation software to demonstrate the action of an integrating loop. In this case, it's a level simulation, for example, liquid level in a tank. And what we're doing is manipulating a valve that adds liquid to this tank. The green line on the trend is our process variable or tank level. Right now our valve is in manual mode, 50% open, and you can see how the process variable is pretty stable. We're going to do an output step change in manual mode, an open loop test, to see how the process responds. So I move the valve up to 60% open, and we're going to watch and see what the process variable does. And we can see the process variable is rising. What's important to note is the way that it rises. Unlike a self-regulating process, we're not going to see the process variable naturally attain some new equilibrium value. Rather, what we're going to see is a continual ramping of the process variable up until the point where the tank overflows. Now it's fairly slow at this point, so I'm going to add even more percentage to my valve and show you a more aggressive ramp. So the valve's going to go up to 70% now. We're going to watch this process variable ramp become steeper. This is a textbook example of an integrating process. We're now adding more water to the tank, and presumably there's a constant draw of water coming out the bottom of the tank. I say water, it could be any liquid. There's a constant draw of liquid coming out the bottom of the tank. If we add more liquid into the tank than we're taking out, the tank naturally integrates over time and accumulates liquid level, which is why we're seeing the process variable continue to rise with no sign of abating. Now, to further prove this is an integrating process, I'm going to take the output in manual mode and go back to its original value of 50%. In other words, we're going to put liquid into the tank at the exact same rate we began. When I do that, and you see the output go back to 50%, I want you to pay close attention to the process variable. It does not start coming down. Rather, it holds where it is. That is one of the hallmark features of an integrating process. We're now balancing mass flow into the tank and out of the tank, and as a result, the tank simply holds its present level. Classic integrating process response. If I move the valve in manual mode down to 30%, we see the tank will begin to integrate down. I'm now losing more liquid out the bottom than I'm adding in the top, and as a consequence, I'm losing liquid over time and my liquid level decreases. Once again, we should note this is not a function of the controller's tuning. The controller here is in manual mode, so it's taking no control action whatsoever. What we are looking at is a response of the process. We're looking at the physics, the dynamics of the process itself, and this particular process is an integrating process. Once again, to prove it's integrating, I'm going to go over here to my manual output on the controller and move it back to 50%. Now I'm adding liquid to the tank at the same rate I was at the very beginning, and once again, lo and behold, our process variable simply holds its value. I'm neither adding additional liquid to the tank, nor am I losing additional liquid, and so the liquid level holds steady. Classic integrating process response. To control this, we are going to find that our controller works phenomenally well with a large gain value. Because this process naturally holds whatever set point we want, so long as we go back to our original valve position of 50%, we will find that a proportional only controller does a remarkably good job of controlling this process. We actually do not need integral action to achieve new set point values. All we need to have is proportional action so that when we make a set point change, the valve position will change temporarily, either adding more liquid to or taking liquid away from the tank. As the tank level integrates and approaches the new set point, the valve goes back to its original position, which is precisely what we need in this process to hold the brand new set point value. In other words, we do not need a novel valve position to achieve novel process variable values. Therefore, proportional only control works great. So I'm going to go over here to my gain and put in a gain of, I have a gain of 1 right now. I'll keep it at 1. We're going to throw this into automatic mode. When I do that, you're going to see the yellow line pop up, which is my set point value, tracking with process variable. So now we begin at 0 error. I'm going to give it a new set point value, let's say 70%, and we'll see how the process responds. The set point steps up. The valve begins on an upward step. That's the way it's adding more liquid to the tank. The valve position begins to close as the liquid level rises. This is precisely what we expect from reverse acting proportional only control. And as the liquid level rises and gets closer to the new set point value, we see that the output will slow down and we just basically ease into the new set point value. It's going to take a while because we don't have very aggressive gain in this particular tuning. We only have a gain of 1. So we will get to our new set point, but it's going to take a long, long time to get there. What will help us out is a more aggressive gain value. So I'm going to take my gain value and go to a gain of 5. 5 times more aggressive than what we have right now. I'll enter the new gain value. We see the valve step up even more, and then the process variable approaches set point at a much more rapid pace. And notice as it does, as the PV achieves the new set point value, our valve position goes back to pretty much where it started at, around 50%. And it will remain at set point there because this is an integrating process, and it's happy to hold level when we move our valve back to its original position. I'll even add more gain here. Let's go with a gain of 10. Notice I'm not adding any integral action, no derivative. I just have a gain of 10. Now I'll give it a set point change. I'll call for this to go to 40%. Set point, yellow line goes down to 40%. Notice the valve, the white line, goes all the way down to 0. We've fully closed the valve, which adds liquid to this tank. And we can see the level is integrating downwards at a rather fast rate, meaning we're draining liquid from the tank and adding nothing to it. As we approach the new set point, we're going to see the valve position come up. There it goes. The valve position comes up and eases into its original position, its bias value of 50%. And you can see that our process variable achieves this new set point with no overshoot whatsoever, even with a fairly aggressive gain of 10. I'm going to show you what it looks like with a gain of 20. Let's go twice as aggressive. I'm going to go to a set point value of 60%. Set point steps up. Valve slams open. It's now adding water to the tank as fast as it possibly can, and we can see the level in the tank naturally integrate upwards. As we approach a new set point value, what's going to happen is the valve position comes back down to its original bias value. And a little bit of overshoot there. The process variable settles right into the new set point value very rapidly, and our valve is right back at 50% where it started. Once again, being an integrating process, putting the valve back at its original equilibrium position means we hold the level wherever we're at. So we see here an integrating process does phenomenally well with a high gain value in the controller with no integral and no derivative action. In fact, integral here would actually hurt us because integral action, when it sees an error, continues to wind the output in one direction or the other. And that in this process would actually guarantee overshoot. I'm going to show you this. With a high gain value, I'm going to put in a small integral value. Let's say 1 repeat per minute. I'm going to go to a new set point value of 40%, and we'll see what happens. I move my set point down. My process variable now is integrating downwards. My valve is fully closed. But what's happening here is integral actions also helping to wind that valve in the downward position. When we reach set point, it takes a little bit before the valve opens back up, and when it does, it overshoots and then comes back down, because during this time when the process variable was over the set point, integral action was winding down, and it was basically taking the bias value of the controller and reducing it. That meant that we actually undershot the set point, which meant that proportional action had to pick us up, and integral action too, and start to wind the valve output back up. And so in other words, we end up with this undershoot after a set point change precisely because we have integral action here. This is a phenomenon you're going to see in any integrating process. If you put integral controller action on an integrating process, you guarantee overshoot or undershoot on set point changes.